Thank you. Fasten your seatbelt. We are taking off. Okay. Changes have always pros and cons. But rapid sea level is the only one which is just a terrible threat. Though in fact utterly wrong. Kod era, det var Strandlund. Okay. It's obvious why we need to keep the information correct. Okay? Sound evaluation, good economy, good planning, good economy. And this is why we are here today. We don't need exaggeration, we need ignorance. And I will try to enlighten this, I hope. So let us begin with a story on the not rising sea. Why would sea level rise? Yeah, it's three ways of rising sea level. If the ocean volume would increase due to glacial melting, if the water column would expand due to heating, if the water masses would move laterally, currents rotation, all these facts can be handled as to rates and amplitudes, as again, which I have to demonstrate. Okay. We go to the frames of how much sea really can rise. The rate of glacial eustatic rise, eustatic means the whole globe, after the last ice maximum was 10 millimeter per year. That is 1 meter per century. Remember that. And this sets an ultimate limit of possible changes at the present setting. This is the limit in rates and in amplitude. Inside, we may play inside. That is where IPCC is. This is what has been recorded in the last 300 years. But anything outside is simply outside. It's not realistic. We can kick it out. And here is the recent figure of 1.6 meter in 100 years, which Madame Hildegard in the Copenhagen said, oh, it's so important. Why is it important? It's against physics, it's against geology, it's against ethics. It has nothing there to do. We have to be inside here. Okay, so that handled the glacial eustatic. Could be saying, but not really. Then we come to the heating of the expansion of the column. Okay, this is the meter of the water column. This is the expansion rate, and this is the various temperature degrees of heating the ocean surface. Obviously, you cannot heat the whole ocean. You can heat it 300 meters maybe, or 300 meters here, or 700 meters have been measured. But then we are down here still. So in the whole of the ocean, those 6,000 meters deep, we will never have the whole 6,000 meter column heated, because that's why it's layered. And the water down here by C14, it's thousands of years old. We know that. So we have to be at the surface level. So if you heat 300 meters by 2 degrees, which is really very much, very, very much, you get a 10 centimeter rise. Okay? If you then go closer to the shore, where it is 100 meters depth, there's nothing more to expand. It's only 3.5 centimeters. It's not very much. And if you go 10 meters, now it's where you start to be swimming. It's 3.5 millimeters. So what's that? And if you come to the shore, it's simply zero, my friend. It's zero. And because there's nothing to expand. And some people think that the water here will flush into the coast. This is not physically correct, because the ocean surface is, by its dynamic forces, very irregular. So we have handled the second. Now we take the distribution. We take the El Nino event of 77 in the 77. You have a 30 centimeter higher here, 30 centimeter lower here. March and in December, this bulge had moved there. Rise, fall here. So it's laterally. And this happened on the short-term scale. It also happened on the long-term scale, which I showed long ago, 1984 I showed. Something super. So those effects are the three variables which we are talking about. Sea level changes. The true facts are to be found in nature itself. Certainly not in the modeling. I recently published a paper in 21st Century Technology and the Great Sea Level Humbug. There is no alarming sea level rise. You can get it. It's also a paper which has been printed by Christopher Monckton, unfortunately forbidden to be distributed. Wonderful, we are back in medieval time. But here it is, and you can get it when we are on our way out. So, I will go through the nature itself. It means the blue point. It is superimposed on the satellite altimetry from 92 to 09. And we may always later cast the 0 point. So let us go through this map. First, Vanuatu and Tuvalu. It is 8 millimeter per year and 3 millimeter there. What does it say? It says absolutely no rise, neither in Vanuatu or in Tuvalu. It's a straight line. Where is this 8 millimeter per year? Not in the field at any rate. We go to French Guiana, which is an extremely nice place because it has 50 years record with very nice symmetric 18.6 year cycles, the tidal cycle. We must cover more than one tidal cycle in order to know where we are going. And this has 3. And it's a stable, it's variation on a perfectly stable 0 line. So it's 0 rise. At the same time, satellite altimeter gives 3 millimeter per year in the same area. There is a message in this difference. Okay? And I don't tell you which difference message. Then we go to St. Paul's Island, because there we had a beautiful sea level record in 1876, because Venus was passing in front of the sun, and they recorded it. And after 135 years, where are we today? Where is the rise? It's gone. Then we come to my favorite place, the Maldives, which is doomed to be flooded by so many people and disappearing from the surface of the earth, not least by the president. So I have a record, very detailed record. We have been studying it in detail, 7,000 years, 5,000 years sea level record we have in detail, and I have cut this part because here people can enter the place. And people survived even 1 meter rises. Those rises and falls, they are redistribution of water rather than rises of the volume of water. Of course, we are interested in this part. So I give you something, 1, 2, 3, 4. It says here, it's a lake, and we have mean tide level, high tide level, a higher high level, which is this one, and another level up here from 400 years ago. We go to the beach, this one, this fall here. It's interesting. Here we have coastal erosion. Coastal erosion, people say, is because sea is rising. However, look here. It's rising here. What happened with the sand here? It's being deposited outwards, downwards, downwards. So it is a sea level lowering. The old beach on pre-1970, it's here. You see the beach ridge. And we have wonderful lakes, which we have drilled a peat bog. It was covered by a lake, sea level rose. We have C14H's of the sea level dried out because sea level fell. We have double rock cut platform, and we have a tree, this marvelous tree, which we have been stable in this delicate position for a long period of time. Let me show you the double rock cut platform. This is the rock cut platform from this period, and we have a map of 1922. Which shows the sea here. Today the sea is here, and you can see where it's cutting. It's still in the process of cutting. And it's not approaching inland. It's stable, and it has been stable in the since 1970 about, which is interesting. Then we come to this delicate tree as a position where you nearly could blow on it and it would fall over. So when I saw this, I told the people, local people, the government, look here, this tree is fantastic. It shows that sea level has not been rising. And we can have been there in this pair for maybe 40, 50 years. So when we came down back there, this is my group, and this is a tea house where we used to sit and look at the tree and love it. Once I came back there with a Danish director for a movie, and the tree was lying down, still green, 2003. And I said, wow. And the scientist, I said, wow, I was wrong. My first impression. So I was, yes, you can always be this. And then I talked to the people, when did the sea take the tree? They said, no. The sea didn't take the tree. It was a group of Australian scientists which pulled it down by hand. Nice people.
Thank you.
Yeah, there are some good guys also, which compensate for it. You compensate for it. Okay, so if we then generalize it in the last 400 years, you have these ups and downs, and this is a prediction for our group in the future. So if we go in the last 100 years, will be a return to this place, if I'm right. It will be a return to this if IPCC is right and we add a little to them. And there was no problem. They didn't even notice those things, the local people. So really, there is no real problem. And the president may be in the sea, maybe under the sea, but the threat is really gone. So let us go to 5, the Laccadives, because it's just north of it. It's the same geology. And the local people in Laccadives testify that no traces of sea level rise are to be found, that they are amused by the story of the president in Male, and they understand it's all a matter of money. So after a fall in sea level 40, 50 years ago, just as in the Male, sea level remains stable. Here is the overgrown old surface. Now terrestrial snails are coming in. This is the new one. And that has not advanced. Just stay there as it has done in the Maldives. Now we go to the most notorious place, Bangladesh. The coast looked like here. And the IPCCers say, coastal erosion, sea level has been risen. But go to the facts, back to the facts. Here we have the trees. They have horizontal roots. What does that mean? It's mangrove trees. How do they live? They live like this, with a mudflat here, above it. It means that it's very, very easy to reconstruct the mudflat before the erosion. It's here, and you can see the delta surface, just a little above. So it's sea level, it is tremendous erosion, but zero rise, my friends, zero rise. So we get the sea level curve over the Bangladesh. Oh, sorry. So, this is the high tide level. There is even a higher one. And this is a picture very, very similar to the Maldivian curve, though in another area. But there is no global rise in sea level in Bangladesh. Forget about it. Then we come to India. India, we were, in the previous slide, we were here in Bangladesh. Now go to Bombay and a tide gauge on the other side. You have tide gauge record. It shows a stable period, a rising period, a fall, and a stable. Remember a fall? We saw it in the Laccadives, we saw it in the Maldives. Here is the fall, very nice, and it's rise and stable, stable. So it's the same picture coming out wherever you go in the Indian Ocean, which is also interesting. Now we go to Qatar. Yeah? It's a very beautiful morphology, because you can see that it is 1, 2, 3 cycles of high sea levels. This one we have dated at 5,000, that's another thing. Exactly the moment of the flooding in Europe, which is another thing. And then you have the second, and this one. The interesting thing that is completely stable. It shows no traces whatsoever of overwashing. There's no traces that sea is rising. Instead, we get a very good that sea has been stable. Then we jump up to Venice. Venice is very interesting, not just because it's a cultural place, but we have there a present record and an old record of sea level. And this is subsidence. It's subsiding, slowly subsiding. It means slowly subsiding. If sea level would be rising, we could immediately see a departure from this line. Immediately. What do we see here? It's no tendency whatsoever. The only thing we see here, at about 1970, something happened. And all over the oceans, 1970, 72, 73, things happens. And like Svensmark says, 77, with some delay. Something happened there. But here we have a very good test area. No rise, certainly no acceleration. So then we go into northwest Europe. I love that area because we have uplifted Fennoscandia. The periphery of uplifting Korsør is a place where is the hinge. It has been stable for 8,000 years. And there at the tide gauge of Korsør, it's no rise. Okay? It's rise up to 1930 because that's a universal rise. And then we have the subsidence trough, Amsterdam, Cuxhaven, and when you come to England and Scotland, up again. Okay, so let us look at the... I take the Cuxhaven 160 years record because I had earlier Amsterdam, but it was finished here because they moved the tide gauge, and that's not good enough. So the difference here is exactly the one which we calculated 1973 for the eustatic factor in the North Sea. So we can get the local subsidence. Having done so, we can subtract and get the eustatic factor of sea level. So not rising in the North Sea. This is the rise after the end of the 19th century up to 1930, 1940. After that, it started to flat out. And the fantastic thing, it's even going down. It's even going down. How interesting. And we have this Amsterdam, then Cuxhaven, and it can be changed. And if you check this portion, which I did long ago, with the length of the day, if I had Amsterdam, it's the length of the day predict a 10 centimeter rise for the deceleration we experience, and a lag time of a few years, a couple of years. So that fits very nice. And we will later see what's coming out here. So if the sea level rise of 3 millimeters for the satellite would be correct, Amsterdam and Cuxhaven would be uplifted. Woo! Complete nonsense. At impossible rates. At impossible rates. So it's you can test this. And we get tired of all this nonsense. Okay? And then we come to the zero level, because now I have shown you all these plots, and there are many more to show you. But this other one I have worked intensively with. It questions the zero level here in satellite altimetry. So let me say something about that. Satellite altimetry reading, it has to be adjusted something, and if you adjust it, you come to what I think zero. In the first satellite altimetry measurements in 2000, both produced by the satellite bodies, they had a curve lying in that thing. In the Grace new satellite gravity measurement, the raw data are here. So they fits a very nice no rise, zero, which fits the observational fact in the field. Then here, in order to get Grace from raw data to calibrate the data, they got it here, and they had calibrated the rise, the satellite data. So this is calibrated, and therefore we know that all of this was calibrated. Exactly what they have done is a bit hidden, but this is the calibrate, but it's personal. It's not based in physics. So I don't like that. I like this, and then the equation, so to say, goes together. And if we remove the correction, we have no rise, like in all the places I have shown you. Then we go to Earth rate of rotation. If sea level would be rapidly rising, following the law of angular momentum, a physical law, the Earth should experience a deceleration. Deceleration is this way. Acceleration is this way. Why this is not the case? Why is this? Because sea level is not rising. Thank you. And then, of course, wait. You can also see something very interesting, because here at 1973, you have a big change. Slowing, rising. And this is where, Svensmark, up with your hand, this is a bit interesting for you also. And so we come here, conclusion. There is no sea level rise recorded. Maldives, Tuvalu, Vanuatu, Bangladesh, and Paul Island, French Guiana, Venice, North Europa, and a lot of other stations. Thermal expansion is small, less than 10 centimeters. And this is very important. 0 at the shore. Satellite altimeter records no or just a minute rise if I do what I have been doing. And then we go back to the beginning. Conclusion. No alarming sea level rise. That you get good planning and good economy. Okay? Sea level rise and flooding, you are bound to go and run into problems, according to my opinion. And of course, you don't care. That's a very bad thing to do. So we should care, but then we should debate it and have a fruitful debate and showing different things, like we are doing here. Why? Because we are in a scientific environment and should keep it a scientific. Because science can sometimes deteriorate into things when you forbid people to do things and show papers and so on. There are a lot of lies and exaggeration linked with global warming. People may behave so, but trees don't lie. That's very important. This is the tree I showed you. It doesn't lie. But you have to pull it down in order not to see it, if you don't want. And this tree, there's no rise in sea level. You see it by itself, your own naked eyes. Nor do we lie. We are sniffing, observing, recording. These are 2 monkeys viewing Kilimanjaro. Don't worry, my son. The present is a reflection of the past. Nothing more, nothing less. Just the same old story. And then it's interesting that The Heretic was a play which Richard Bean did about somebody studying paleogeophysics. Who could that be? Which had found that sea level was not rising in the Maldives and got into a lot of troubles. And when the play started, and they had to change my sex, but Diana, at least, she was clever, and she said, the last years have not been easy. In the middle of my personal hell, I have not hell, I have had a lot of fun. Something happened. I've changed my opinion of the stars. I've decided that the stars are rubbish. And I don't mention any stars. I just thank you for the minutes I have shared with you. Thank you.
Well, thank you, and I thank the Howard Foundation for having the initiative to organise a meeting like this. It should have been done 30 years ago, because in that 30 years, science has been dreadfully damaged, a point I come back to later. My interest is in old rocks, and my interest is in what happened in the past. And the one wonderful 4-letter word which has rarely been mentioned today is time. People have given us the long-term record of 100 years. In 100 years, it's like looking at the frame of Casablanca, of that one love scene, and you look at that and then kill off the rest of the film. Oh yes, of course, that's a love film. It isn't. It's a very different story. And the story is that we are very uncertain about the numbers which are bandied around. And these are numbers of original carbon dioxide coming from the mantle. That's why we have carbon dioxide on other planets. It goes through a sequence of cycles. It gets captured, it gets naturally sequestered. And it's this cycle that I want to look at, because we have at present a very small amount of carbon dioxide in the atmosphere. It is a trace gas, but that was not always the case. We have had up to % carbon dioxide in the atmosphere, and it depends upon who you read, but it could be up to 20% carbon dioxide in the atmosphere. What has been happening over time is that carbon dioxide in the atmosphere has been decreasing, and it continues to decrease. And we hear, and we've heard a couple of times, mention of volcanism. absolutely and totally erroneous. There are some dozens of volcanoes that are measured. This is because they are a health hazard. There are millions of volcanoes that we don't measure. Yet those which we measure, we've had to change the figures because volcanic degassing doesn't occur during the eruption. It occurs before, during and after the eruption. We have about 1,500 active volcanoes. We have to revise the figures all the time because we're getting more and more measuring stations. We've only heard today about terrestrial volcanoes, and these are volcanoes where we get partial melting of the mantle that is fluxed by carbon dioxide. As a melt rises, it degasses. When the melt comes to the surface, it has very little carbon dioxide in it, one or two exceptions which I'll mention later. But well before an eruption, you lose carbon dioxide, and that process is well known and well established in experimental petrology. So it is a process of degassing that has taken place since the beginning of time. We can see this in modern volcanoes, and we can see an intriguing relationship between the amount of volcanism and the amount of carbon dioxide in the atmosphere over time. So there is a very close relationship between volcanism. However, these are the volcanoes that people look at. They look at volcanoes like Krakatoa, a volcano that I climbed on my 60th birthday because I could, and a volcano that emits a lot of gas. We measure these gases from a few volcanoes, and the weather-changing volcanoes are really quite pathetic. I'm more interested in the bigger volcanoes, but you can see these Chilean volcanoes top right. There's a fracture that controls the leaking out of these molten rocks. That fracture is leaking gases. Bottom right is a rock that was originally a carbonate rock. It has since been replaced by silica. This is very good evidence that after eruptions we're still leaking out a lot of carbon dioxide. We have beneath the Antarctic ice sheets a number of volcanoes. They are having quite a dramatic effect, and they have erupted in the past. There would be a very significant change on planet Earth if they erupted significantly again. But the real volcanoes, the ones that are the elephant in the room, the ones that people ignore, and we heard it today in two talks, are the submarine volcanoes. These are along fractures in the ocean. This is where we're pulling apart the ocean or sliding the ocean, and it is these volcanoes that give a very characteristic type of melt. These are pillow lavas. They're balls of molten rock that flow along the sea floor. Those rocks chemically react with seawater. You can see that in all pillow lavas of all ages, going back thousands of millions of years. So why is that so boringly important? It is because the reaction of seawater and volcanic rocks is a buffer. The oceans have been buffered since we first think we had oceans 4,000 million years ago. And those buffers are minerals in seafloor volcanic rocks, minerals in sediments, plus an internal buffer in the oceans. When we run out of rocks on the seafloor, we might start to think about acid oceans. Until then, don't wait up. And it is quite misleading for people to flap their wings and talk about the oceans becoming acid when there is an alkaline ocean. The oceans are extremely variable in their pH, and we have natural buffers that are operating all the time. We see it with these sort of rocks that I just showed you and I tried to go back to, but this is the northern hemisphere, so it doesn't go backwards. And look, it doesn't happen today, it's happened in the past. We've had supercontinents in the past pull apart, degas, huge amounts of basalt, like the photograph on the right, coming out at the surface. These have been degassing as they've been rising. When you pull apart continents, you degas. It's a very common phenomenon. What we never hear about are volcanoes that don't belch out lava. These are volcanoes that are gas volcanoes. These are Mars. And these are extremely important because these are the sort of deposits, if you're looking for element 79 in the periodic table, you very commonly get these around gas volcanoes, and there's been an extremely large amount of research done looking for element number 79. If you want it, come up and have a closer look. It's on my periodic element tie, but most of you would know it's gold. And there's been a lot of work done on gold and gas volcanoes. Here's one of them. This is Takhta Suleiman up in northwestern Iran, one of King Solomon's mines. It was around a gas volcano. The crater's still there. And what was the gas? Carbon dioxide. These are extraordinarily common. They don't go into any register where people measure the amount of carbon dioxide being released into the atmosphere. But then we have some supervolcanoes, Tobar bottom left, Yellowstone to the right. And these are very, very significant volcanoes. Taupo is even greater, and we pray for Taupo to erupt again because that's the only way we're going to beat the All Blacks. It'll take out all of the North Island, and a good thing too. These are supervolcanoes which put a lot of aerosols into the atmosphere, but they're not the big ones. The big ones are the basalts, and we have supervolcanic provinces of basalt where they emit masses of aerosols. It is probable that 2 of the 5 major mass extinctions are related to massive volcanicity. But they're not the big ones. There's even bigger ones. We see these flood basalts around the Red Sea. These basalts had their melting point lowered by dissolving carbon dioxide. As they rose, they leaked out carbon dioxide. If you sit at a basalt volcano measuring the amount of carbon dioxide coming out, sorry, you're too late. It's already come out, and it will continue to come out in small amounts later. But they're not the big ones. The really big ones are beneath the sea floor. And these are the supervolcanoes, which are huge plumes. A point that has not been mentioned is that when supervolcanoes change the shape of the ocean floor, you actually change sea level. And these have been very rarely looked at because they're hard to get at. We know where they're there, and we know from experimental petrology what carbon dioxide does in these. So let's look at some of these. When we have an eruption, we leak out gas before, during and after. There are 64,000 kilometres where we're pulling apart the ocean floor, and every year we heat 10,000 cubic kilometres of seawater to cool a molten basalt from about 1100 degrees Celsius to, say, 2 degrees Celsius. That is enormous heat transfer. That fluid moving through the basalt chemically reacts with it and buffers the ocean. So don't give me this codswallop about ocean acidification unless you want to change the pulling apart of crustal rocks. And then we have a reference which is very conveniently ignored with some bathymetry that's been done in the Pacific and then a projected figure. And these are for the seamounts, ancient volcanoes, the things that Darwin published on in 1842, where he was arguing that if you had a relative sea level rise, in other words, a coral-rimmed volcano, and it subsided, that the atoll kept growing. You don't get inundation of coral atolls by a sea level rise or a relative sea level rise. We knew that in 1842. Why have we forgotten it? But what we do know is that there are millions of seamounts on the ocean floor, and these seamounts have erupted, they have leaked out carbon dioxide, and they are still leaking out carbon dioxide, and we get some areas, such in the Arctic Ocean, where we've had very large submarine eruptions with huge amounts of dissolved carbon dioxide, like 13.5%, and we had to cool those rocks. And you can only cool those rocks with circulating seawater. These volcanoes are not measured. We have not one submarine measuring station, and yet we see the results of it thousands of years later. So for me, the science is extraordinarily uncertain. When people are trying to do budgets of carbon, I think they really should add ice blocks to their drinks. A place where I've done quite a lot of work is the island of Milos, top right, the Greek islands. If they had the drachma, it would probably be wonderfully devalued now and you could afford to go there. Top left, gas explosion vent. Top right, gas explosion field. What was the gas? Carbon dioxide. I sit there in the ocean, in the hot springs, with carbon dioxide bubbling up through my strides and telling my students about wonderful hot springs. All those white rocks are from hot water reacting with rocks. These are chemical reactions that have precipitated carbonates, top right, and given us sinters that used to have a lot of carbonate in them. None of these go into the equations that we use for the carbon balance. Why? Well, I would like to know. Pamukkale on the left, you probably have been there and know it. Travertines in Turkey, again, huge precipitation of carbonates from warm springs. And on the ocean floor, we have hot springs, bubbling out carbon dioxide. We have pools of liquid carbon dioxide on the sea floor. Do we ever see any of those in the mass balance equations? And we see artesian waters, top left, nice and warm, bicarbonate waters, shallow water hot springs, black smokers, again with a lot of CO2 in them, and the result of this is precipitating sulphide rocks, and the white material in that is carbonate. So we have a huge amount of CO2 that has been shifted around. We've known about this, and we've known that it's taken place for thousands of millions of years in hot springs like the left, where we had carbonates. This is underground in the Philippines, where we've got generations of carbonate veins cross-cutting each other. So CO2 is a major component of volcanic exhalation. It's probably the second most abundant component, the most abundant being water vapour. And we can go to places like Death Valley, evaporites, carbonates, bottom right, ancient evaporites, 1800 million year old evaporites. We've locked up a lot of carbon dioxide in rocks. These are rocks where Lord Monckton went to, I think a year or two ago with me, a wonderful area of rocks that were granite, that were 12 kilometres down, that have leaked out huge amounts of carbon dioxide, have been uplifted, are still being uplifted, and have their daily earthquakes. And every time you have some major geological activity, you leak out gases. We have carbonate volcanoes. These are the ones in East Africa. The bottom left is how you can find these things. They've got a very distinct magnetic image. They have zoned rocks around them where carbonate has reacted with rocks. These are rocks that spew out carbonate lava. They do not go into the equations. We can see here, we go back to the Red Sea. Top right photograph is where we've had gases streaming through liquid basalt. Bottom right is where those gases have precipitated carbonate in the cavities. So CO2 is a major component coming out of volcanoes. It always has, and it always will. We just happen to be in a period of volcanic quiescence. But we see over geological time there's quite a distinct relationship. And who would have thought of it? Every time you get an earthquake, you get a great release of carbon dioxide. That has never gone into any of the calculations. This is a well-known earthquake from Iran, where during the dilation area in the red, we had a release of warm bicarbonate waters and CO2. And every time you build mountains, when you squeeze rocks and compress them, you dewater them, you lose carbonates, they get reprecipitated, the top two photographs. A very common process. Dewatering gives us bicarbonate alpine springs. And if, as we heard earlier, carbon dioxide floats around in the atmosphere for a long period of time, then we have a serious problem. And there are one or two calculations that might show this, but the bulk of the calculations show that atmospheric carbon dioxide sits in the atmosphere for a very short period of time. It gets taken out of the atmosphere by life, by geological processes and by sediments. All of these sediments are carbon-rich sediments. They've all got more than 5% carbon in them. They vary from age, from being a couple of 100 million years old to a few thousand million years old. They are full of microorganisms. They are full of the fossils of the major life on Earth. And the major life on Earth, it's not whales and it's not trees, it's bacteria. And they, again, do not enter any carbon balance equations. But we know that these bacteria have been active for a long period of time. These are calcium carbonate rocks deposited by bacteria. Again, a little bit younger. Again, a little bit younger. These rocks have got 44% carbon dioxide in them. And these have been deposited from bacteria. And then we had a glaciation. Now, we heard today about 2 glaciations. Well, I'm sorry, folks. We've had 6 major ice ages, within which we've had glaciation and interglacials. These 6 major ice ages were initiated when the carbon dioxide content in the atmosphere was higher than now, in some cases much higher. 2 of these ice ages were at sea level at the equator, like this one here. some 800 million years ago. These two might have been at a period when the sun was a little bit faint, but the more recent 4 major ice ages certainly were not with a faint sun. So we heard a story about the Ordovician glaciation. Sorry folks, it's wrong. When we look at the bottom photograph, we see glacial rocks. These glacial rocks formed at the equator at sea level, and then on top of it is a carbonate rock called a cap carbonate as a result of sea level rise, and not the pathetic sea level rises you people have been talking about. We're talking about a real sea level rise of 1,500 metres. And there's extremely good evidence from Namibia and other places that at the end of this glaciation, or probably 3 or 4 periods during this ice age, sea level went up and down by more than 1 kilometre. Furthermore, these cap carbonates have an isotopic signature saying that seawater was very, very warm. And we can see that some of the carbonates associated with these glacial sequences in those 2 scenic photographs. Each one of those hills contains more than 40% carbon dioxide. These are dolomite rocks, and you can only precipitate dolomite when you've got a high partial pressure of carbon dioxide. So these are telling us that we had very high carbon dioxide in these times. And here we've got a Great Barrier Reef, not wiped out by ocean acidification because CO2 was much higher at this period of time. It's thoroughly enjoyed itself being a barrier reef and now fossilised. And if you look into the distance, you're probably looking about 40 kilometres. All of that rock has got 44% carbon dioxide in it. That's where it's gone. It's gone into sediments, like here in Guilin in China, like here in southern Victoria, still younger, like here in some of the rocks where we can measure with mass spectrometry some of the fossils from seafloor sediments, showing that we've got cyclical changes, but we also tie up huge amounts of carbon dioxide in life. And today we tie it up in coral reefs, stromatolite reefs to the top right and the bottom. We heard earlier in Andrew Watson's talk about being tied up in soils. The white stuff in those soils is calcium magnesium carbonate. So we haven't got the sums right. We probably know the chemistry quite well of putting carbon dioxide into seawater. Most of the carbon dioxide in seawater can be in 3 forms, but this is the diagram you saw before that I want to come back to. In this diagram, we have evidence over time that carbon dioxide firstly has changed and has probably gone down very significantly. On this diagram, which represents the last 542 million years of life, and bear in mind that's just a little bit more than 10% of life, and life of the planet, and bear in mind that for the bulk of time this planet has been warmer and wetter than now, and bear in mind that in the geological past ice is very rare and we are living in an ice age. When we look at this, we can very clearly see the sequestration of carbon dioxide into rocks and into sediments. There are 4 glaciations that are, or 4 ice ages represented on this diagram. We heard one at the Ordovician, possibly high carbon dioxide, a massive one at the Permian. Again, the carbon dioxide content was higher than now. Another one in the Jurassic, carbon dioxide content higher than now, and the current ice age, which has been going for at least 30 million years. In each case, more carbon dioxide in the atmosphere than now. So we cannot appeal to a faint sun for fairly modern glaciations. So let's look at some of the changes that have occurred there. These changes, you can draw these lines. The end result is we are lowering carbon dioxide in the atmosphere. Why? And we heard it earlier. We've had a blossoming of life. And the coals have sequestered a lot of carbon dioxide into the atmosphere. Plants have, from the atmosphere into rocks. Plants have only been with us for 10% of time. They're Johnny-come-latelys, and they have been the final straw that broke the camel's back to pull all that carbon dioxide out of the atmosphere, because it's been very rich in the past. So we are relatively starved. And we look over time, and we see that temperature has gone up and down. On that scale, and note it's a log scale, all it's telling us is it's quite common to have temperatures go up and down. It's especially common to have rapid temperature changes during periods of glaciation. And this we see here. We can see there are very rapid changes in the oxygen isotope record, suggesting that there are very rapid changes in temperature. that is quite normal. But the key thing is, are any of the absolutely pathetic minuscule changes that people measure today, are they in any way larger than things of the past? Well, the answer is no, definitely not. And this is a well-known diagram showing our interglacials and our glaciations, and notice that during the glaciations we've had huge fluctuations in temperature. As we heard before, that happened in the Little Ice Age. But even though temperature's fluctuating, it was cold. It was very cold. Is there anything unusual about today? Well, I'm sorry, it's a two-letter word, it's no. We saw this diagram. On that scale, we see something very interesting, and it's a black material. It's dust. And we see in the geological record, every time it's cold, every time we get a glaciation and lower latitude areas are not covered in ice, we get deserts and we get dust and we get aeolian deposits. We see that in the ice sheets. It confirms what we see from the past time. But what we do see is in ice, we have fluid inclusions. These fluid inclusions in the ice tell us that there is a very significant change, and that change is temperature rises followed by a rise in carbon dioxide. That is quite commensurate with the solubility of carbon dioxide. It is the exact opposite that you had heard this morning. And if that is the case, then we have to start to have a very significant look at variability. And when we look at the past, when we look at since the last glaciation, we've had massive variability during this glaciation, and now we don't have much variability. So I don't get frightened. If I was in the Younger Dryas, what a wonderful time to be when it started to warm up. It was extremely rapid. And when we look at history, we see that we have depopulation, famine, and the plague hits us in cold times. In warm times like now, we thrive. So, thank you. I'm just getting worked up. So, when we look at history, we see that there have been warm times, and in these warm times we had great empires develop. We are in one of those warm times, and it's a strange thing about temperature. It goes up and it goes down. And just because it's going up in our life doesn't mean we're driving it. Temperature has been going up since the end of the Little Ice Age, since the Maunder, actually. What a surprise. We've come out of a really cold period of time and temperature's going up. I mean, I'm totally gobsmacked. It's very hard to accommodate that view. And the Little Ice Age here, we can see temperature has gone up quite significantly. So I've looked at geological timescales and shown with glaciation and with ice ages that there's little relationship between carbon dioxide and temperature. We've shown that we don't really understand the variability of carbon dioxide, and there are huge uncertainties there. But we can also look at historical times and modern times. And in modern times, in 1940, we really started to burn hydrocarbons. And since 1940, we've had a six-fold increase in the burning of hydrocarbons. And if we believe the IPCC figures, then 3% of the annual emissions of carbon dioxide derive from human activity. I would like to know, and I would like someone to show me, how that 3% drives climate change, yet the other 97% doesn't. I would also like to see, when we've had these periods of warming and cooling while carbon dioxide has been going up, the rates of warming have been the same. One would have expected, if it was driven by carbon dioxide, then the rate of warming would have been fairly high from 1977 and onwards, somewhat similar to Niels's Venice diagram. So we don't see that. And so if carbon dioxide is actually helping to keep the planet warm, it's very, very hard to see. No doubt that we humans are putting carbon dioxide in the atmosphere. No doubt that we humans are changing the surface of the planet. But are we heading towards catastrophic climate change? Well, I wonder, because the Earth always changes. For people to call people like myself a climate change denier is a public advertisement of their total and absolute ignorance. because geology is about change. It always changes. You look at a rock and you try to say, well, what was the climate then? It's quite normal to have massive climate changes. There's nothing special about today. I know it's damaging for your ego, but there's nothing special in the world we live in. Because carbon dioxide is fabulous. I was thinking flying over here, what a good chap I am, putting all this plant food into the atmosphere and making the crops thrive. It is the gas of life. We probably have about 1,000 ppm CO2 in this room at present. You are breathing out 4%. It is a wonderful gas. Without it, we are dead. We have this huge cycle, and we are two-bit players in that cycle. Carbon dioxide doesn't stay in the atmosphere for too long. It's got better things to do. And the last point I want to finish with was that I think the cacophony we've had about climate has damaged science. It has damaged science dreadfully. In a previous life, I took exception to another group of people who damaged science, and they were the creationists. I was engaged in litigation for just over 10 years with 9 defamation actions, which I'm sure you're not surprised about. None of those ever got to trial, which is a tragedy. And to make sure that these people who were frauds got their comeuppance, I hit them with 2 cases. One of copyright, and the second was under the consumer protection laws, misleading and deceptive conduct while engaged in trade and business. Because the climate catastrophists are engaged in trade and business, or trade and commerce. There will be someone out there who will take people on, and that person will take them on because the catastrophists, in my view, are very similar to the creationists. They are blessed with faith. They ignore time. They ignore this huge body of science called geology. You ask a creationist for the primary data. You can't get it. Well, doesn't that sound familiar? It's a cash cow. And the creationist businesses are huge cash cows. If you ever want to start a religion, come and see me, because I've got all the legal documents done. You can make huge amounts of money. And they pass a simple message. We're all doomed. Repent. Pay the rent. Pay up. And we will give you salvation. And they use consensus. And they frighten the politicians. I think science has been greatly damaged. If we'd had one of these conferences each year for the last 20 years, we would not have damaged science. And we should not even be talking today, because the argument has moved on. It's no point in talking science. The punter knows that the cake has been over-iced. The punter has moved on, and the punter will frighten his politicians, and this conference should not have been necessary now. It should have been necessary 30 years ago. I think science has been greatly damaged. Thank you.
Well, thank you. I'm not quite sure where to start. One thing, I don't do drama. But what I will do, I'll tell a story. Some of you may have heard this. There was a physicist, an engineer, and a mathematician, and each in separate bedrooms. And we'll start with the engineer. There was a fire in the waste bucket. So the engineer sees the fire in the waste bucket. He sees the fire extinguisher. So he gets up, he takes the fire extinguisher, and being an engineer, he wants to make sure the fire goes out. So he just sprays all the foam on the fire in the bucket, and the fire goes out. Now, a physicist treats this differently. A physicist wakes up, sees the fire in the bucket, sees the fire extinguisher, calculates the trajectory he needs to get the foam into the bucket and how much foam he needs, presses the button, and with the minimum amount of foam, puts the fire out. The mathematician wakes up, sees the fire in the bucket, sees the extinguisher, knows there's a solution, that it exists, and he goes back to sleep again. Now, it's a bit of a mathematician's joke, I should say. Now, the reason I tell this is that different people come from different backgrounds. And we've had a geologist, Ian's given us really lightning tour through the geology of history. And, of course, he's used to dealing to very long periods, but the period I'm dealing with is something like 50 to 100, perhaps 200 years. And that's minuscule in terms compared to a lot of the times that Ian's talking about. And timing is everything, because at different time scales, different things are important. We also have chemists. My brother's a chemist, so I hope I'm not insulting everybody here. And chemists, know about solubility of CO2, and they know about solubility of CO2 in the ocean. But unfortunately, they don't know that much about CO2 in the atmosphere, and therefore sometimes misunderstandings happen. Engineers, well, engineers have to, they're asked to find a solution to something, and engineers find it very difficult to deal with uncertainty, and quite rightly. I mean, Mike and I have had a lot of conversations about this, because if you're going to make certain of something and you're very unsure about it, then you have to spend extra money, and that comes to the economics. And the economists are very dubious about models, and quite frankly, looking at economic models, I'm not surprised. And it's not that it's not that the economists are poor at modelling. It's just they've got a very difficult subject. They don't have the rules of nature that we have to limit what we do. So that's the start. I just want to say a little bit about my background. I did a degree in applied maths and then a PhD in atomic physics. And just coming back to different approaches, my subject was very much based on the Schrödinger equation. I had a nice bit of theory to work on. We then used a numerical method to solve that equation, and I was looking at the scattering of electrons by atoms, and we used a thing called R-matrix theory, and then we had observations. And it was very clean. When it comes to looking at weather and climate, it's much more difficult, and that's probably where I want to start, because first of all, we don't have total closure in theory. We have a lot of constraints and conservation laws that we are constrained by. That affects the modelling. And then, of course, the observations are not just simple observations. You've got lots of natural climate variability and so forth. Satellites don't actually measure temperature, they measure radiation, so you have to try and deduce through a model what the temperature is and so forth. So if I can find how to start this. I'll start a bit about natural variability, because there's some implications for that, for how we interpret the observations. What might change climate, the greenhouse effect, a bit about climate models, and if I have time, a bit about sea level, and something about attribution. In fact, I may skip sea level, but we'll see how it goes. Right. Well, we know climate varies. Climate varies on all time scales, and Ian's made that very clear. It varies on very short time scales as well. This is a thing called the North Atlantic Oscillation. It's not really an oscillation. It's a statistical measure. Sorry? Hold on a minute. I'll tell you in a minute. These are anomalies of easterly and westerly wind. So what you can see is that over the last 100 years, over Western Europe, the predominant wind in winter has varied from year to year. And you can see in the last year, we actually had a very strong easterly anomaly bringing cold wind off the continent. Now, this is probably just unforced natural variability. And that's what dominates local climate. And we know this happens, and we know this is in equations of motion. Somebody mentioned Lorentz earlier. And chaotic behavior isn't unpredictable. It's just very difficult to predict, because any small error in your initial conditions grows very quickly and makes it unpredictable. So you have to be very careful of that. And sometimes you can see here, this is the original Lorentz attractor, but he did do something which is very similar to east-west wind, showing similar sort of behavior. And you can see there are periods when it moves between one regime and another. And has somebody got a pointer? Just make it slightly easier. If somebody can find me a pointer. Thanks, Ian. That one. Thank you. So you can see periods here where it stays in the same regime and then it changes. Now, of course, this was actually on a model of convection, Bernoulli convection, and it's based on a set of simplified equations. But this is the principle of why the atmosphere is chaotic. Now, this shows global mean temperature from anomalies from a simulation with a climate model. I think it's one of the older Hadley-centric climate models. And you can see this same variability. It's not all due to chaos. Some of it's due to just stochastic effects and so forth. But what you can see is, and this is over quite a long time scale, so we've got about 800 years here, but a lot of variability, which is just totally unforced. It's just the natural variability of the system. And you can see periods where there are quite marked changes and so forth. Just to put this in context, that's the change in global mean temperature up to, I think this was up to about 2000. These dates are meaningless for the model because nothing has changed in this. So that is the problem that we have, is detecting any change due to a particular cause against this unforced variability. That's true for everything, whether it's solar changes, whether it's volcanoes or whatever. Now, 2 points to make on this. You cannot look at a 10-year trend and really say much about what's happening and what's causing what's going on. So to look at the effect of something like carbon dioxide, you're going to have to look at something like at least 50 years to have a reliable trend. It won't be reliable statistically. So people who look at 10-year trends and what's happening year by year, it's interesting for different reasons, but it's not really telling you much about what's happening underneath. And you would not expect to see a close correlation between radiative forcing and what's going on a decadal timescale. Now, the second point I wanted to make, I've forgotten what it is, but I'll probably come back to it. It's just slipped my mind. Never mind. Now, this is the global mean temperature record. I think it's pretty similar to what Phil showed. It's based, I think this is relative to the 70 to 90 average. And so, I've remembered the point I wanted to make before. I apologize for this. The second thing, it was a point somebody said, you can't make any predictions with a chaotic system. Rubbish. What Lorenz talked about was prediction of a second kind. So what you can't say is that in 50 years' time, you'll be on whether it'll be here or so on. But in the case of greenhouse gases, if you put a large enough forcing, this envelope of this variability will be moved upwards. Now, in a very simple case, look at the difference between summer and winter. Summer and winter are always different, but every winter varies and every summer varies. And that's because of the change in radiative heating. It's a very extreme example, but that's really what we're talking about here. If you change the external forcing, you will shift this. And you need to shift it enough so you can detect it against the variability. Just to say that the observed record shows a lot of variability on different timescales. Some things like the 98, 99 El Nino, we know what the cause is. Some of the volcanoes, particularly Pinatubo, El Shishon, and the Mount Agung. Other of it is just really, on this time scale, it's unpredictable noise. It's a natural variability. Just a final point. I showed global means, but of course, on a regional scale, things vary a lot more. This shows a temperature anomaly last December, and you can see the extreme cold we had in this area here, also in Alaska. But this is balanced because all the atmosphere changes. The blocking, which I think somebody else talked about, is moving air around. It's colder here, but it's warmer there. It happens to be over Greenland, and it's warmer here. This, again, I think is relative to 1971 to 2000. So although it looks like there's not much change in the global mean here, it neglects the trend before that. So this underestimates the warming since the beginning of the last century. Right. Factors affecting climate. If we're going to look at that, there's certain things as a scientist I would want to know. I'd want to know what the magnitude of the radiative forcing was and how it changes with time. I want to know what the expected effect on climate was, on the patterns, and how that compared with observations. And I'd probably be interested in some predictive capability, but that's a bonus. So let's look at the main factors that we know have influenced climate in the past. And this shows the major eruptions. Here you see Pinatubo, El Shishon, Agung. And you can see we've had a period in the early part of last century where it was very little. This is essentially sulfuric acid, which is pumped up into the stratosphere where it stays, and it has a cooling effect. And you can see over the last 3 or 4 decades, 4 or 5 decades in fact, the effect of volcanic eruptions has probably been to cool climate. You can try and quantify that on a decadal scale. Individual volcanoes may cool by about 4 watts per meter squared. On a decadal scale, it probably averages out to about between 0.1 and 0.3 watts per meter squared. And as Ian has said, one big volcano can actually spoil your day, and we can't actually predict these things ahead. So any anthropogenic projection is subject to that uncertainty. We then looked at solar cycle variations, and we can see in the period where we've had measurements, and this is the output from the sun, you have to divide by 4 and multiply by about 0.7 to get the forcing at the Earth. And you can see there's been although you can see the solar cycle, there are different estimates of this. This is through satellites, so it's probably the most reliable estimate we have. Again, there's no trend. So the direct heating, if you look at isn't big enough to explain some of the changes we've seen. It's certainly much, much smaller than that due to greenhouse gases. Now, that's why Henrik has looked at what the effect of radiation of changes in solar output might be in cloud, because, as he points out, if you get small changes in cloud, those can have quite an effect. And he showed the ISKIP data. What he neglected to tell, and I presume because of time, is actually, when you look at the raw ISKIP data, it does this. And, of course, this, I think what Henrik did, and he's in a much better position to answer this, he used another satellite to try and collect this. But certainly, I would like to use this data to try and validate our models, and I just find it's unreliable. Trying to look at low cloud, and that's what's important for this effect, is really very difficult. So when we look at solar, over the time scale of 100 years or so, the orbital changes are pretty negligible. And that's what we think explains changes in ice ages. If you look at the total irradiance, again, that's very small. It may have local effects, and that was one of the things that Mike Lockwood referred to, because it may, through ozone, have some effects in winter. And then the question of cosmic rays and clouds, well, first of all, I would question just how well we understand the relationship, how low cloud has changed. And then, as Mike pointed out, even though you may see effects in the solar cycle, when you look at cosmic rays over a multi-decadal time scale, they're not changing very much. In fact, they're changing in the wrong direction to explain any warming. Okay, so that's quantitatively what the size of estimates the size of these various forcings. When you look at greenhouse gases, and I'll go on just to illustrate this, we know pretty well what the forcing is. We know the radiative transfer, and Andy said a bit about this, and I'll say a bit about it later. And from pre-industrial values, we're getting a value of about 2.6 watts per meter squared. There is some uncertainty in that, but it's very small. And then probably where the big uncertainty in the anthropogenic effects is the effect of industrial aerosols, which have at least two effects. First, they directly reflect sunlight, and secondly, a very similar effect to the one that Henrik's positing for clouds, but in this case we do know through ship tracks and so on that this thing actually does work. So in terms of quantitative estimates, this, it's a very simple thing, and if scientists try and find the most simple explanation, and this is the biggest single forcing. Now, greenhouse effect, and Ian's pointed this out, it's a very bad name, and this is a very bad explanation, but essentially the sun heats the earth, some of that heats the ground, transmits it to the atmosphere, and then the atmosphere absorbs some of the radiation, puts it back at different lengths, and some comes back to the surface. That's actually not a very good explanation. And I seem to have lost some slides here. Never mind. I wonder if I got the wrong version. Okay, and Francis earlier on actually gave a much better explanation of the greenhouse effect. I do suspect I've got the wrong set of slides. And I think... Can I just, so I know what's happening? No, we're all right. We're okay, sorry, I'm panicking. Okay, so, they just come in a slightly different order. No. It's okay, I can zip through that. Probably the easiest way to do is this. So, and where's this one? Right. Now, essentially, if you were to look at in fact, I'll go on to the next slide, and this is what's been confusing me. The greenhouse effect that is called, you can present it in two different ways. One, you can look at it as a difference in temperature, or you can look at it as a difference in radiation. If you look at the surface temperature of the planets, Mars, Earth and Venus, this is what you get. If you then take a satellite and measure the long-wave radiation coming off and treat it as a black body, this is what you get. So the difference is the greenhouse effect. That's due to the fact that long-wave radiation is being trapped in the atmosphere, being radiated from a higher but cooler level, and hence warming the planet. So you can see on Mars, which has a very weak CO2 atmosphere, you've got a greenhouse effect of about 3 degrees. If you look on Earth, which has a lot of water vapor and carbon dioxide principal radiators, you can see you've got a warming of about 33 degrees. And if you look at Venus, which is a very dense CO2 atmosphere. So any idea that increasing CO2 doesn't increase warming, it's got about 470-degree greenhouse effect. So, I mean, you just have to look at the planets to know that what we call a greenhouse effect is real and effective. Just want to draw your attention to this, that the more carbon dioxide or greenhouse gases you have in the atmosphere, the higher the mean level of emission. So it's about 1 kilometre for Mars, about 5.5 kilometres, which I think Francis mentioned this morning, and about 70 kilometres for Venus. You can't see the surface of Venus in the infrared, it's just so dense. Now, we know the properties of these gases very well. We can actually measure them from space, let alone from laboratories. These are the equations. I'll not go into this, but it's one area of the radiative science is very well known. And when we look at the Earth's atmosphere, this is from a paper by Lakis, we can work out what fraction, to fair accuracy, of the greenhouse effect on Earth is due to water vapor, cloud, and carbon dioxide. And what you get, there's some uncertainty because these things don't go together linearly, so you have to make some approximation to do this. So about 20% of the current greenhouse effect is due to CO2, about 30% due to cloud, and about 55% due to water vapor, the rest due to other greenhouse gases. Now, this is important because on short time scales, this is a feedback. If you warm the atmosphere, you're going to increase water vapor. If you reduce it, you're going to cool it. And that's important to remember. The other point I wanted to make, and people have said, well, these are only trace gases. Water vapor varies in concentration, obviously, markedly, but it's about 0.2% of the atmosphere, and this is about 0.03%. All the other gases, carbon, nitrogen, oxygen, and so on, have no greenhouse effect. So that 33 degrees is due to the trace gases, water vapor, and CO2, and that's important to remember. The other comment I'd make, Ian was saying, well, you know, CO2 is a nice friendly gas, and it is. Let me talk about oxygen. If you were to double the concentration of oxygen necessary for life, probably we would combust. So the fact that this is important doesn't mean more of it is necessarily a good thing. A little bit more might be, too much might not be. Same's true as chocolate, by the way. We can look at the absorption, so we don't have to depend on laboratory data. This shows essentially, if you're in a satellite looking down, you can see this is what the absorption would be if we had a black body. This shows the absorption by water vapor, which you can see separately up here, by ozone, by carbon dioxide, and by water vapor. The reason carbon dioxide is so effective, it sits right in the middle of the Planck function. And that's one reason why it's such an effective radiator. Now, the other thing is often said, well, carbon dioxide is saturated. And they showed the very detailed line structure that you get, and this is just one line. So for weak concentrations, this is absorption. So this is no absorption here, this is total absorption. And this is the variation in wavelength about a single absorption line. And as you go from weak to strong absorption, you do saturate the center of the band. But then the band broadens, and you get further absorption. So there's no particular limit to the effect of CO2 on climate. This is well known. And the reason this means that for low concentrations, you get a linear increase. For a stronger concentration, it goes to approximately a square root. Here, it's approximately logarithmic. It's not exactly logarithmic. And if you go to much more dense concentration, you get some weaker lines, and it goes back to being close to linear again. I did have a problem with your book, Ian, but maybe we can talk about it later, because basically, you double CO2 concentrations each time to get the same temperature increment. And that's taken into account in the models. Right, this was known to Arrhenius. This is an older version of my talk, but I can manage with that. So we know what the effect of doubling CO2 is radiatively. If we treat the Earth as a black body, which is basic classical school physics, you get a warming of about 1 degree. If you allow, assume water vapor varies at constant relative humidity, there's some debate about that, but not a lot, then you would bring this warming up to about 2 degrees. Now, the water vapor thing, I think Andy talked a bit more about it. Basically, one of the basic classical laws of physics is that the saturation vapor pressure of water increases exponentially with temperature. So as you warm the surface, you're automatically, all other things being equal, and that's a very important caveat, you're going to get about a 6% increase in evaporation per degree warming. In practice, it doesn't turn out as much as that, but in the atmosphere, you do get effectively, we believe, constant relative humidity. Then there are other lapse rates. Some of these have been estimated from models. You don't need a model to do this bit, and that's where the large uncertainty comes. I've been quite conservative in this because in estimating this from models, you assume that they add together linearly, and nonlinear effects, when you actually look at the models, you get something more in the line of 2 to about 4.5 degrees. Just going back to the water vapor feedback, this shows water vapor over sea surface temperatures. It's quite an old paper, and most of this stuff was done in the 1980s, 1970s. You can see that the water vapor in the boundary layer at least very much behaves as you would expect from the clouds-disclopere annihilation. You can see in the tropics it's a bit higher. The subtropics where you've got descent, it's a bit lower, and in our latitudes it's a bit higher again. And that's a result of atmospheric motion. Okay, clouds. We talked a bit about clouds. They cool climate because they reflect radiation, and that's why Henrik, particularly low clouds, is interested in the change in low clouds. High clouds, on the other hand, trap long-wave radiation. They're responsible for that greenhouse effect that you saw. And one of the reasons why we get this uncertainty models is that these are pretty difficult to model. I mean, they've been included in models since about 1978, and we're constantly trying to improve them, comparing with satellite data. And as the satellite data, satellites become more, have better instruments, we now have vertical radars and so on. There's a lot more we can do to understand that, but that's another talk. Now, in terms of climate sensitivity, it's obviously, yep, thank you, very important just how big an effect that has. And this is actually taken from the last IPCC report. And I should stress this is a mixture of models and observations. So I think Gregory and Foster, for example, looked at estimates of forcing at the top of the atmosphere, which I should say is problematic. Even over 20 years, we do not have a reliable record of the change in solar input to the atmosphere. And if we were going to do one thing to try and help this, it would be to have reliable satellite measurements of the Earth's radiation budget. So all of these are not just pure model, but they all show the same characteristic curve that if you take the middle value, you have a peak. As you go towards very low sensitivities, that becomes much less likely, but there's a long tail on the high side. So the medians on these different things, somewhere between 2, some as high as 4 degrees. This is actually much higher. In practice, I mean, I've seen estimates from models as high as 11 degrees, but when you look at the simulation of present-day climate of those models, you could easily rule them out. But in this range, it's very hard to discriminate them. But 2 to 4.5 is probably about typical range. I'm obviously not going to get through all of this, so just say a bit about models. They're based on laws of ordinary physics. There's some empirical aspects guided by physics, observations, fine-scale models. Tested against weather forecasting, recent climate, past climates. For example, we looked at the last glacial maximum in the Holocene. Sometimes useful. And you have to realize a model is a model. But I think sometimes people really underestimate the power of models in understanding. Observations on their own are not particularly useful. Just say a couple of things. They're not wholly empirical, and they're not statistical fits to past data. The basic equations, just for those of you who are mathematicians, the Navier-Stokes equations, essentially Newton's equation of motion, conservation of heat, or the first law of thermodynamics, the perfect gas law, conservation of mass, hydrostatic equation. So we do have an advantage over the economists. We have some very heavy constraints on what our models can do. Right, I'll probably finish after this and make a few comments. Hindcast attribution prediction. What you've probably seen is pictures like this. This shows a model simulation where we just included natural factors, and that's the green curves. And here there have been several model simulations because, as I said before, you cannot predict climate within that envelope of variability, but you can see the effect of different volcanoes. This shows the observations. And similarly, when you include anthropogenic effects, you find that you get a much more consistent fit. But this is only the tip of the iceberg of evidence on attribution. And that is an old slide. I can see where we are now. First of all, the changes won't be uniform, and I think that's an important point. And there are patterns, and I'll show later just the horizontal. It turns out the horizontal temperatures aren't very discriminating between different causes of climate change. But what is more discriminating is and I'll go on to the next one. And I apologize, this isn't labeled, so I'll talk you through it. These are the vertical changes in zonally average temperature. So this is the North Pole, this is the South Pole, and this is going up. This is about the level that planes fly at. And this is for 4 different sets of model simulations. This is 2 sets of observations, and this is a model simulation over the same period. This is actually for, if I get this right, this is solar. So when you change, if you increase solar input in a model, this is the pattern you get. This is for volcanic aerosols, so they heat the stratosphere, cool the lower atmosphere. This is greenhouse gases, which warm the upper stratosphere and cool, warm the troposphere, cool the stratosphere. This is ozone, both tropospheric and stratospheric ozone, cooling the stratosphere, warming the troposphere. This is direct effect of sulfate aerosols. They reflect radiation back up, which is absorbed in the stratosphere. And this is when you put them all together. Now, this is for, I think, 1890 up to 1999. This is for a more recent period because we only have radiosonde observations from about 1950. So these are basically from about 1955 up to, I think, 2006. I think this is the Hadley Center data set. This is another one from another radiosonde data set. And this is a model simulation. These are on the same scale. And what you see, you only get this cooling when you include greenhouse gases and ozone. You don't get it with some of these other factors. And that's one of the reasons why you can use the patterns to help discriminate what the cause of recent warming is. Certainly, you can see the warming in the troposphere over the 50 years of radiosonde measurements. Now, there has been an issue in the tropics because just on basic physics, you expect to see a warming increase with height. Essentially, if you bring moist air in the tropics up and it cools, it condenses out water. And so the temperature profile in the tropics is it increases with height much more rapidly than in a dry atmosphere. And on this, that's essentially the dotted curve. The band is from model simulations. I think they've been normalized. These are probably simulations of the last 50 to 60 years. And the curves are 4 different radiosonde sets. And in the past, this has been an issue. And it certainly is something where there's still something to understand. But basically, over a 50-year period, not over the last 20 years, the models and the observations are pretty well consistent in the vertical profiles. I think I'm going to have to stop. Yeah, okay. I was going to say something about sea level, but I'll just draw to conclusion. I have a couple of questions. In terms of sea level, we've evidence, and in fact, Henrik showed this, of the ocean heat content increasing, so we know that's happening. We know that most of the glaciers, except perhaps those in Europe, are reducing. So we've got 2 inputs of water into the ocean. So sea level isn't rising. Where is it going? Simple question. You can't just turn the curve like that. It'd be great if you could, but never mind. I would say more on that, but maybe we can do that in discussion. I probably said enough, but there's a lot more I could say, and I can say it in discussion either individually or later. Thank you.
Thank you very much.